Are there any questions for me that I can answer?
Good driving.
Okay, let me mute everyone upon entry. Alrighty, that's fixed now. Okay, so my neighbors have construction, so if it's too noisy, let me know and I will put my headphones on. But I noticed when I had my headphones on, I speak more quietly, and then in the recording it's kind of weird. So yeah, I will put the headphones on, but let's try it without them if possible. Okay, so basically I want to now take a moment to reflect where we are in this course. Remember when we started this course, I had this structure. I divided it into three uneven parts. First part was basically a quick warm-up for everyone to be on the same page regarding machine learning and deep learning. And then we had a long sequence of lectures all relating to large language models. We started with some background, like what is the language modeling task. Then we looked into main components of large language models, starting from transformer architecture, pre-training, instruction fine-tuning, alignment through RLHF or other algorithms. And then we had a long chunk of lectures that were all connected to how we are using these models in practice. We had things like how to make the inference and training of these models more efficient. We had the lecture related to safety of LLMs, regarding memorization and privacy, and so on. And there is way more to say about large language models, but there is also a place where we need to stop, which is today. But I do want to mention a few things that we didn't talk about that are more advanced and interesting if you are, thinking about staying in this space, be it in practice or as a researcher. So there are things such as relating to efficiency of LLMs. For example, we talked only about the transformer, but there is also another architecture, namely a mixture of experts that is emerging. Also, another architecture stays space models that I didn't put on the slide here. There are different kind of attention mechanisms that people are developing, such as grouped query attention, to make everything more efficient. In terms of the development, I did mention a little bit about scaling laws, the idea of predicting how much performance of your LLMs would change if you continue scaling the number of parameters of the model. And more recently, there is a new idea which is called test time scaling, where you are not scaling the budget you have for pre-training the model. Rather, you are thinking about how to best use the budget you have at the test time, where you can use more complicated algorithms for decoding your tokens that will lead to better outcomes. So if you have used the most recent model produced in the OpenAI o1, you've seen that it generates this kind of planning tokens, and you can kind of see a little bit of its reasoning in a plain English. In terms of applications, today there is a huge interest in developing agents, such as web agents or computer agents, agents that you can instruct in natural language to do something for you, such as make me a spreadsheet that, I don't know, contains some information and does some operation in it. And this agent takes that utterance and is able to make a plan and execute that plan to produce, an outcome you want in the real world. In terms of evaluation, there is way more to talk about evaluation. One thing that I wish I could have talked about is the idea of data artifacts. These are these shortcuts in your training data that the model exploits, and it can use these data shortcuts to come to right answers, but for all the wrong reasons. And it seems like the model is capable to do some very, very complicated reasoning tasks when in reality just learn to these data shortcuts that your annotators have introduced. And then in terms of the safety of LLMs, there are so many more things to do, like watermarking outputs, editing knowledge, interpretability, jailbreaking, many, many other topics. However, we have only 4 more lectures before the overview lecture in this course, and it would be really bad if I didn't mention a few more classic NLP things for you to kind of know finishing the NLP course. So we need to use the time to go over those. And the first topic, okay, before I dwell into the first topics in this space we are going to talk about, I just want to mention that before large language models, before we were just expecting the model to kind of implicitly gather all the useful skills in their parameters and find a way to use them, we would actually previously had approaches where we would make a structure from input text that will help the model to come to the right answers. So, for example, here, this is a classical NLP pipeline where you have your text that's as with large language models is going to be tokenized into sequence of tokens. Before a subword tokenization in 2016 for languages like English, that usually meant split it into words. And then at top of each word, you would first do things like assign part of speech tag, which basically is a tag that tells the grammatical role of a word in a sentence, such as is it a noun or a verb, for example. And we are going to learn how to do part of speech tagging today. Then next layer would be a parser that will give you more information about the syntactic structure of a sentence, such as if you have, for example, subject-object-verb, subject-object relation, this could be derived from the parser. You would also do things such as labeling whether a phrase in a sentence is a named entity that refers to a person or organization, and so on. And so on. After you had this, sequence of additional information on top of your words, which we called structure prediction, you would only then do the tasks such as sentiment classification. So you would gather all of this additional stuff, and only then, based on that information, you would have algorithms that would then infer what the let's say if the task is sentiment classification, what the sentiment label is, unlike what we have done so far in the course, where we have just gave a sequence and got the label or another sequence out without providing these additional layers of information. So now, your first reaction could be, well, Anna, why are we going to then learn how to do all this extra stuff? Like that's a lot of extra work, and we have implemented some of these things ourselves during, our assignment work, where we didn't need to do any of that, and the model learned to figure everything out. I think there are 2 things I want to say here. First, in terms of we are learning all about this in a class called NLP, and I think it's absolutely necessary for you to finish this class knowing what some of these things are, even though you might not use them later on. It's a meta language that's going to be useful when you talk to other people in the space. So that's one reason. Another reason is that, yes, these things still can be useful even in a large language modeling world. So Matre had shown you this illustration that shows that many languages in the world actually don't have even the unlabeled data that you can use to, do the next token prediction to pre-train a language model, or they don't even have labeled data to learn these downstream tasks. So for certain languages, you have these very low resource settings, and these kinds of tasks that you have been doing in your assignments and learning in this course, you might approach them for well-served languages like English in a way that you do not need to provide any extra additional information, and the model will kind of learn everything implicitly through pre-training. But for some languages, you don't have that opportunity, and doing this more classical NLP approach might be more viable for you. Again, learning these tasks will be useful when you compile data for task, even if your task is English, because you might want to ensure that there is significant linguistic variation, and you do need to know what the noun and verb is and what part of speech tag is, and so on. Or if you're doing evaluation and then your model is failing, you are going to do error analysis where you're going to inspect for which kind of phenomena your model fails. And then again, having this language coming from structure prediction will come in handy. In some places, in some companies, they do not care to have the fanciest algorithm there is. What they care is that they have good performance and that you can explain how, why did your, approach fail or not. And that all is more feasible if you have these approaches built on these syntax, on these linguistic structures, because if you don't have a neural network approach where the solution is hidden in the model's weights, but rather explicitly written code, then it becomes easier to do debugging and so on. And for some tasks, having that kind of approach might be sufficient. You might not need the LLM. So this is all to say that there is value in knowing this. And ideally, if we had enough NLP faculty or faculty that are teaching ML and deep learning courses, we would have both the NLP course that's, going into the details of classic NLP and provides more and more topics, and an LLM course that you have had an opportunity to take. Okay, so all that said, we are now going to start this sequence of these 4 lectures. And today we are going to learn about 2 classic sequence labeling tasks and one classic non-neural supervised approach to solving these sequence labeling tasks. And the first task is part of speech tagging. So to understand what this task is, we need to understand what our part of speech is. Part of speech, or we say POS, is a category of word which is based on the grammatical relationship of this word with other words in a given text, or its morphological properties about its affixes. So, for example, a grammatical role of a word in a given text can be that it's noun, or a verb, or adjective, or so on. And what we mean by morphological properties about affixes is that every word has its stem, which is the part of the word that carries its primary lexical meaning. It's often a root or a base form of a word, like, let's say, a verb play has its base form, it's just play, right? But then you can add suffixes to the base form of the verb play, such as ed, to make the past tense form of the verb played. So affixes are these morphemes. Remember, morphemes are the smallest units that still have some meaning that are attached to a word stem to form a new word or new word form. And morphology, again, remember we learned this well back, is relating to the forms of the verbs. So you can add suffixes or prefixes to change the form of the verb. Okay, so part of speech categories of words based on grammatical relationships or morphological properties. Okay, I have put here some fun facts about some languages, but I'm going to skip that. I think I want to cover way more in this lecture. When we talk about grammatical relationship of a word in a text, we should consider that there are 2 classes of word, open and close. Closed class words have relatively fixed membership with respect to their grammatical role in sentences, and meaning and new words in this closed class words category are rarely introduced. So these are words such as function words, short, frequent words with a grammatical function, such as determiners, a and the. We rarely introduce new determiners in the language, right? Pronouns, similarly, prepositions, these are all close class words, and they will have very specific deterministic, meaning always the same grammatical role in the sentence. In contrast are the open class words, which are continually being created or borrowed from other languages. And this includes word types such as nouns, verbs, adjectives, adverbs, and interjections. I won't go over this because it would take forever, but I do want all of you to sometime after this class, this lecture, to open Juravsky and Martin's section 17.1, where they define many types of words. And you should familiarize yourself with these types of words. I think things like nouns and verbs, pronouns are pretty clear what they are because these are things we are commonly introduced to. But then there are more maybe newer types of words such as complementizers or copulars or modal verbs. It's good to know what these are because, again, you want to build that meta language such that when you are talking to other people, you have shared vocabulary because they might say this is a modal verb and you want to be on the same page. So please check section 17.1. What is important, and I didn't say, is that open class words, unlike these closed class words, do not have a clear grammatical role in a sentence always. So, for example, let's look into this sentence. I will book a room at a hotel. Here are all the possible grammatical roles each one of these words can have according to the Pentrim Bank tag set for part of speech tags. So these tags in this column, these are part of speech tags. And this whole collection, this whole column is called a tag set, which is defined by someone. And you will have different tag sets for even the same language. For example, okay, I don't want to show you this. We will see in a few slides another kind of tag set for part of speech in English. So I want to do a little exercise with you. Let's look into each one of these words, and you will tell me which part of speech tag I should label each one of these words. So for the word I, which part of speech tag over here I should use? Maybe use the number to make it easier for me to follow along.
Is it 18?
Yeah.
Personal pronouns, yeah.
Yeah. So I here is a personal pronoun. And yes, we are going to use the tag PRP, which is in the 18th row. Okay, the next one I will say that even I am not sure whether it would go under a modal or one of the verb forms. So let's say it's a modal verb, but I'm not 100% certain. Okay, so now we have the next one, book. Which part of speech tag we should assign to the book here?
Is it 27?
27. Yeah, exactly. So we are going to use part of speech VB, which stands for verb-based form here. However, if I gave you another sentence here, which part of speech tag we would assign to book in this sentence?
Would it be 12?
Yes, that's right. It's gonna be 12 because this is a noun in a singular form. So what I've tried to illustrate here that you had the same word, which is book, which in one sentence it was a verb, in another sentence it was a noun. And this is exactly what I wanted to say in the previous slide where I said that this open class of words might have different part of speech tags depending on the surrounding context. So when you're doing part of speech tagging, there is we need to sometimes resolve some ambiguity, such as this ambiguity of whether the book is either a noun or a verb in a given sentence. All right, so this brings us to the part of speech tagging task. Part of speech tagging is the task of assigning a part of speech to each word in a given text. This means that you are going to have a sequence of x1, x2, xn, which are going to be tokenized words. And you are also going to get a tag set. Tag set is, as I said, it's a set of possible tags, such as Pantry Bank tag set here, which has 36 possible part of speech tags. Why I am emphasizing this is because different people have defined different tag set. There isn't universal agreement of how broad or fine-grained the tag set should be. So when you are doing a certain part of speech tagging, you need to specify which tag set you are using. So if you are doing a Pantry Bank part of speech tagging, you do emphasize it's a Pantry Bank part of speech tagging. You can notice here I said words, not tokens, which can refer to, also subwords. I'm saying this because usually these are pre-neural approaches that have been done before 2016 when subword tokenization is introduced. So very often these will be done at the full word level. All right, so this is your input, and your output is then a sequence of label. And this is important to remember that I said a sequence of labels, meaning each one of the words xi is going to get a label which we denote here with yi. So that means you are not providing a single label for the entire sequence. That wouldn't make sense, right? Part of speech tags are the grammatical rules of words. You are labeling each one of these words with a corresponding part of speech tag. So here, Janet is noun, Will auxiliary, back verb, the determiner, and Bill is a noun. So this is an example of sequence labeling task. Or sequence tagging, the task of assigning a label to each unit in a sequence. Unit here is a word, thus mapping a sequence of observations, words, to a sequence of labels of the same length. These terms are extremely important to know. Sequence labeling or sequence tagging, referring to labeling a sequence into another sequence. Any questions about any of this? All right, so you might wonder, although I kind of hinted at why part of speech tagging might be useful when I was giving motivation for linguistic structure prediction in general, but let's go over some cases where it is useful. It can be useful for solving other NLP tasks. For example, when we learn what parsing is next time, you can, and parsing is determining the syntactic structure of a sentence. So not only looking at the grammatical role of individual words, but rather their relationships. Then part of speech tagging can improve syntactic parsing. For example, whether a word is a noun or a verb will tell us about likely neighboring words. For example, in English, nouns are preceded by determiners or adjectives, where verbs are preceded by nouns very often. So this information on part of speech tagging can help syntactic parsing, which is the next step in the classical NLP pipeline. It can also help with tasks such as machine translation. For example, in Spanish, adjectives come after the nouns, and in English, they precede the nouns. So having information about whether the word is a noun or adjective in your source language, being, let's say, Spanish, you can use or introduce a rule in your machine translation system that ensures that when you translate it in English, that adjectives come in before the nouns in your translation. Then it can help sentiment classification. For example, if we know that sentiment-bearing words are really important, and very often in the sentiment-bearing text, this will be adjectives such as inspiring being positive or terrible being negative. So kind of looking at where are my adjectives and adverbs in this piece of text, and then doing additional computations of understanding whether those words are positive or negative can help you build up a sentiment classification system, from bottom up, if you were not using language models, which will figure out all of this on their own. Also, it can help text-to-speech. For example, object can be a noun, or it can be a verb when you say that you object to something. And there is slight variation of how you pronounce this word, depending of whether it's a noun or a verb. So if you, again, have a system that's not end-to-end, then you could introduce this rule that it's determining whether object is a noun or a verb, and based on that is pronouncing them properly. Now, in an LLM world, although I said you will see this for maybe companies that want to have a very clear, control over their systems, or you are working with low resource languages and so on. But you will also see using part-of-speech tagging when you're working with well-served languages like English, if you are interested in something that's called cultural analytics, where you take a collection of texts, which we call corpus, and then you analyze what is happening with words over time. So maybe you have collection of text in some period from some century or many centuries, and you want to check whether certain verbs, how their meaning is changing over time. And for that, it's going to be useful to check whether the grammatical role of those words is changing over time too, just as an example. Okay, I mentioned that there is a prop bank text set. This is another example of a tag set. So excuse me, this is a pantry bag text set, which we have seen before. This is another example of a tag set, which comes from universal dependencies. So for you, I don't expect you to now know every single tag here. If you are implementing this, you're going to, retrieve the tag set yourself. What I want you to remember is that there are different tag sets, and when you're saying I'm doing part-of-speech tagging, that you need to specify in which tag set are you using. Okay, so next thing, how difficult is this? We have talked about, okay, there is a bunch of words which have deterministic grammatical role, and then there are those open class words such as noun and verbs that might have different grammatical roles depending on the context they appear in. So how difficult is part-of-speech tagging? Well, roughly only for 15% of word types, remember types are distinctive words in the vocabulary, are ambiguous. So this suggests, okay, maybe only a small fraction of words are actually ambiguous in terms of their grammatical role, so this can't be too hard. However, those 15% of words, distinct words, are actually occurring many times in English language. Excuse me. So roughly 60% of tokens in some large corpus is going to be associated with these word types that are ambiguous in terms of their grammatical roles. So actual tagging of tokens in your corpus can, this ambiguity becomes a bigger problem because these words are more presented in the corpus. For example, if we have a word back, it can have many different grammatical roles, such as here, earnings growth took a back seat, and here a back is an adjective. A small building in the back, here back is a noun. A clear majority of senators back the bill, back now being the verb, and enable the country to buy back debt, here it's a particle. And also we have it as an adverb. So it has many, many different possible grammatical roles. However, despite this word having 5 different possible grammatical roles, not each one of these grammatical rules is going to be more likely to, some of these grammatical rules are going to be way more associated with the word back in a given corpus. So, for example, I believe that particle grammatical role for back, this kinds of usage of back is way less common than using back as maybe a verb. So what this is leading to is, if not all possible tags are equally likely for a given word, then as our baseline system for part of speech tagging, we can predict for each word the tag that has appeared most commonly with that word in our training corpus. So, for example, for word back, you check for each one of these possible tags how many times that tag had actually appeared in the training data. And for this, you need label data set, where you have both text and part of speech tags written by a human. So you have label data. And from this label data, you check for the word back, how many times each one of these possible tags appeared. And then at the test time, you predict the most likely one as a predicted tag. And this is called majority baseline. The way I just described it is majority baseline applied to the task of part of speech tagging, but majority baseline can be used for any single task. Okay, so if we do calculate majority baseline in one of these labeled data set for part of speech tagging, then this very simple baseline system will have an accuracy of 92%. So it's really, really high. And this is another thing I want you to remember in general. Very simple baselines can have really good performance in your data, especially if your data is skewed in some way. So calculating baselines is absolutely must when you are developing systems, because here your system might have achieved, 78%, and that sounds like relatively high number, but relative to the baseline of 92%, it's a terrible result. So that's one thing to remember. And then another thing I want to say here is that state-of-the-art achieves about 97%. So there is only about 5% improvement that you can gain by doing more eloquent approaches than just calculating the majority baseline. And it's actually a human estimated performance as well. Okay, any questions about anything on this slide or previous slides? All right. So again, just want to emphasize that the concept of majority baseline is a really important concept to consider. All right, so I will go over this quickly. So if we did gain 5% improvement over this baseline by doing some approach that learn things from the label data, you might wonder, where do these improvements come from? Like, what else could a model learn? Well, it can learn that there are very often certain priors for words, so that some tags are more likely than the other, as it's being used in the majority baseline. It can use the information from the neighboring words. So if we use the determiner the, it suggests that the next word is very likely not a verb, for example. And then morphology and word shape also can suggest a lot, such as that having a prefix "un" suggests that the word is adjective. "li" suggests that it's also adjective. And here, yeah. So if we have a word that is capitalized, it kind of suggests that it's likely a proper noun. Okay, so these are kinds of things that the model can learn. And then you might ask me, well, what are the models that people are using for this? And most models are going to be under supervised machine learning, meaning that we have a data set with text where a human annotator had labeled each word with its part of speech tag. At that time, that had to be done by experts, people who understand grammatical rules. And once you have that label data set, then you can train a model on the training data and test it on the test data. There are various models, types of models people have used for this. And today I will use the opportunity, since we are talking about tagging, to cover one classic algorithm, hidden Markov model, to present you how can you do sequence tagging with a non-neural approach in a supervised way. But before that, I also want to cover another classic sequence tagging task before we move into how to actually use hidden Markov model to predict these tags. So are there any questions about part of speech tagging before we move to the next task? All right, I'll take that as a no. So let's move forward. Next task we are going to learn about is named entity recognition. So as a name term says, there is something called named entities. What are those? Named entity doesn't have a very strict definition, but you can think about it, anything that you can kind of refer by a proper name. And most common named entities are persons, such as Mary Curie, location, New York City, organization like Stanford University, or geopolitical entity like Boulder, Colorado. But the term has also been expanded to things that aren't really entities, such as dates, times, prices, and they can also be very specialized to a domain. For example, in biology, we can use named entity system to label genes or proteins or diseases in a, let's say, scholarly text. You will also find that different named entity sets also can have a very different range of specificity. So you can have things like animal, mammal, dog breed. So there is some hierarchy between entities. Often named entities are going to be multi-word phrases, which means that you have so-called segmentation problem. Unlike with part of speech tags, where I told you, okay, you have a unit, so it's let's say a word, and each word needs to be labeled by a single label. Here, you can have a phrase, and you don't know what are the boundaries of the phrase beforehand. So you first need to determine where the entity starts, where does it end, and you also need to give the label to the entire entity that can be, for example, here, 2, 3 words long. So you need to figure 2 things at this time. So this brings us then to how named entity recognition task is defined. It's another sequence labeling or sequence tagging task. You get a sequence of tokenized commonly words and the set of entity types, right? As I kind of hinted before, there are various definitions of what the entity is, and given a certain data set, you will use their set of entity types, and you will need to specify which set of entity types you are using. But once you have these 2 things, then your goal is to label each one of the words with a label. However, here you will notice this very confusing looking thing, which oh, the brackets here are a bit weird. Okay, right. I don't know why I put B and D. Oh, I know why I put B. Never mind. I confused myself for a second. So let me specify what this refers to. As I said, you need to both label the word with named entity type, if there is any, but you also need to figure out the boundaries of the named entity. So to stay in the realm of sequence labeling, where you are labeling each word with something, people have introduced so-called BIO notation, which is sometimes a little bit more expanded, and it might allow additional tags. So focus right now on this one, which is the most commonly used one, BIO. So here you have your entity types such as person, organization, and location. But for each one of those possible entity types, you expand them by creating two additional types by adding this prefix B dash and I dash. B and I dash will allow you to specify where does the entity start and where does it end. And then you have this special outside label, which denotes that this is a word that doesn't belong to any entity. So let's go through this example. Jane Villanueva, I guess, I don't know how to pronounce this last name, of United Airlines Holding discusses the Chicago route. So we can tell this refers to a person, right? So these two words together are a person. And the way we can denote the beginning and the end of this named entity type of the person is by labeling first word with B dash person, meaning this is the beginning of the person entity type. The next word is then inside or I dash person entity type. And then the next word no longer belongs to the entity type of a person, so we use label O. Then we move forward. We have United Airlines Holding. We know this is an organization. So again, we are doing two things at the same time. We are labeling the first word in this entity with B dash organization, suggesting beginning of the organization entity type. And then we have airlines inside, holding inside the organization type. And then we come to the outside, discusses and not belonging to any entity type. And finally, you have beginning of location for Chicago. And then you immediately start to produce as a next label outside because there is no word that's inside this location entity. So this is BIO, the most used notation for named entity recognition. Here you can see the variants IO and BIO-ES. So this one is even more stripped, like you can just say it's inside the entity type, which will become tricky if you have two named entities of the same time, one after the other. Then you won't know where the boundary of the first and where the boundary of the second is. So this is why beginning is useful. And then there is also richer representation with E and S that basically when we have these entity types that are composed only of one word, it is using S for singleton. And here it's denoting the end. And this one is, yes, it's richer, but it's more complicated and doesn't give us huge benefits over BIO. So this is the one you will see a lot. So to kind of wrap, named entity recognition, when approached as sequence labeling task, is a task of taking a sequence of words and for each one of the words predicting the BIO tag with respect to the given set of entities for that word. All right, any questions about this? And I want to emphasize that BIO notation is going to come handy anytime you need to basically label spans and determine the boundaries of spans in text, even when the task is not labeling named entities. So this BIO notation is this a little bit broader technique that we bring into the named entity recognition too. Yes, please.
Yeah, I was wondering, are there any situations where this just always fails? This just does not work? The BMIs, the language is just too complex?
I personally am not aware when this would always fail. Maybe there is something like that, but this is a useful task that's commonly deployed in practice. This is the reason why we teach it. So it certainly is not common to see named entity recognition just failing a lot.
Okay, good.
Okay, so again, as we did with part-of-speech tags, with named entities, there is also words that can have many entity types depending on the context in which they appear. So this is an example of a word Washington that can refer to person, organization, location, or geopolitical entity. So depending on how this word is used, it can refer to these different entities. So the task of named entity recognition isn't super simple, just knowing the word and then using some rule that always returns the same entity. Why it can be useful? Well, similarly to part-of-speech tagging, it can be used as a useful step to other tasks. For example, if you are doing the task of targeted sentiment classification or aspect-based sentiment classification, where you want to not only predict the sentiment, but specify who has that sentiment and towards what, then named entity can be helpful to extract named entity that has that sentiment. So for example, if there is sentence, Janet loves this couch, then named entity recognition would extract Janet as a named entity of a person. It would be, when we learn about parsing, be connected to the word love, which has this sentiment bearing, is a sentiment bearing word. And through all of this, you would understand that Janet is the one that has this positive sentiment toward the couch. It can be useful for question answering or information extraction. And again, similarly to part-of-speech tagging, it can be useful if you're doing any kind of cultural analytics stuff where, for example, here I just imagined an example of wanting to study how British novels depict India during the colonial period. And here named entity recognition can help you to extract what are the locations these novels are mentioning, what are the people, what are the dates and events. And again, similarly to part-of-speech tagging, here you can use supervised machine learning. Again, that means that you do have a labeled data of texts where each word is annotated in a BIOS notation with named entities. And then you can use various supervised machine learning algorithms. But today, imagine how we would use hidden Markov models for named entity recognition. Okay, any questions about named entity recognition before we move to hidden Markov models? All righty. So far you have learned two classic NLP tasks that are we approach both of them as sequence labeling tasks, namely given a sequence of words, for each word produce either part-of-speech or named entity label. So this is the first thing you have learned today, which is on its own important and useful. And you know that if you don't have an opportunity to approach some downstream task in an end-to-end fashion, meaning we just give input and the model gives us output without any additional information, you have learned that the part-of-speech tagging and named entity recognition can be a useful step to building a system that can do that kind of a downstream task if you didn't have end-to-end approach as possibility. So now I want to teach you hidden Markov models, which are a very classic model in NLP. If we didn't talk about language models, this would be one of the most important models that we have learned. And we are going to use the opportunity that we are talking about part-of-speech tagging and named entity recognition to introduce hidden Markov model, although it can be used for tasks beyond just part-of-speech tagging and named entity recognition. So hidden Markov model, or abbreviated as HMM, is a probabilistic sequence model, meaning that given a sequence of units, such as words, is going to compute a probability distribution over possible sequences of labels over the sequences of, let's say, word, and choose the best label sequence. So with part of speech tagging, giving a sequence of word, we are interested to give a sequence of labels. And hidden Markov model is a model that can do something like that. Do you recall when we mentioned Markov before, and when did we last calculate a probability distribution for some potential sequences? Does any of this ring any bell? Transformer or RNN? Not really. We didn't use Markov property in a transformer or RNN.
I'm not sure, but wasn't it the decoder for next token generation when we were talking about beam or nucleus decoders?
No,
No.
we didn't use Markov assumption there. Ganesh?
Was it during n-gram, bigram modeling?
Can you specify a
Where we
bit more? You are missing just a single word. You said bigram modeling. Can you plug in
right.
word?
So for the n-gram modeling, like if we relax the like previous context, like until only like 2 words.
You are right, but bigram modeling is not a thing. Bigram, some word modeling is a thing. So which word are you missing?
I'm not able to recall that.
You have this. I'm 100% sure you know this. This is like mask language modeling. Like I'm testing you to do mask language modeling. Okay, so the word you're missing is language, right? Bigram language modeling, right? Yeah. So what Ganesh has just said when we introduce n-gram language models, where pre-neural language models, we have said, okay, we want to calculate the probability of a sequence of a word, joint probability, which can be written using the Bayes rule or chain rule as a product of conditional probabilities. But when you come at the end position, then we had considered all previous n-n words, which means if you are at the 100th position, you would need to have this long context of 99 words. And we said, well, there simply aren't many bigrams of that size that exist. And that threw off our whole computation. And then we said, well, let's use Markov assumption. And we said, instead of looking at all the preceding tokens, we had said, let's use only 2 preceding tokens, which would refer to the bigram. This would be trigram language model. If you consider only previous word, it would be bigram language modeling. So this is when we first introduced Markov or mentioned Markov for the Markov assumption. And language modeling is the task of calculating probability of a sequence. And if you are using conditional language modeling and, for example, for machine translation, that's an example of where, given a sequence of source token, you want to predict the sequence of target tokens. So this is kind of like what we kind of had imagined in some other contexts before. So I just want to draw your attention that this is not some crazy stuff that are completely orthogonal to the things we have heard before. I do want to go over these things you did mention in the chat just to kind of highlight why those aren't the answer to my question. So transformer and RNNs, both of these were mentioned after we have introduced n-gram language models, and we have said that with transformer or RNNs, we didn't need to stop the computation to preceding few tokens, right? Like with transformer, if you are on a given step, you have consider all the previous tokens when you are doing computation at that token's time. Similarly with RNNs, which recursively are gathering information about all previous tokens. So you didn't deploy Markov assumption there. Encoder similarly is just encoding, looking at everything. There is no limitation of what it can look at. And then frequency, I don't know what exactly is referring to here. We mentioned relative frequency when we did talk about Ngram language modeling as a way to estimate the probabilities. So if that was suggested by frequency here, then yeah, the answer is kind of connected to that, but in a few steps removed. And then beam search and nucleus sampling were just those sampling procedures where we didn't use the Markov property or anything like that. That said, before we actually sample, we are calculating these probability distribution over vocabulary, and that's related to the idea of calculating the probability of a sequence, right? Like we could have used all those probabilities to then find the probability of the entire sequence. So yeah, maybe in that way is connected. So yeah, watch out for these things that again that you are not mixing some of these concepts. Okay, so just wanted to remind you of that. I'm going to here now introduce discrete Markov chain in a very formal mathematical way. So I'm going to just build this very huge definition of a Markov chain. So we are going to start with Q being a set of states or observations. So these are random variables in a probability sense, what you learned way back in your basic probability class. And these random variables can take on some values from a set. So here, the sets we are going to talk about are these part of speech tags or named entities, for example, or with language models, words. One element you need for your Markov chains is a so-called transition probability matrix, where an ij element in that matrix represents the probability of moving from state I to state j. For example, if we are talking about language models moving from a given word to another word, what's the probability of that, which was measured by the conditional probability of a next word given the preceding word. So we want to have a probability distribution for a given state. So each one of these rows should sum to 1. So if we are talking about, if we are in a state 1 and we are interested in probabilities of moving to all other possible states, then this should sum to 1. Another element we need is initial probability distribution over states. So if we are at first position, what is the probability of starting in a given state? So for example, for language web model, if you are at the first position, we are just starting to decode the next probable token, then you have some initial priors of what possible words could be. For example, you won't start a sentence with adjective. It's probably, maybe with adjective, okay, maybe with the verb you wouldn't. But very likely you will start with a determiner because that's a beginning of a noun phrase. Some states may never have any probability and therefore they can never be initial states. And this is where our Markov assumption again comes in. We are using Markov assumption to say that the probability of being in a state X at the ith possible state should be measured by considering all the previous states. But if we deploy the first Markov assumption, then we will just consider where we were previously. Okay, so here I do not want to confuse you. We are just bringing all the elements of the Markov chain into a place, so just mathematically defining it. However, here we are talking about these discrete Markov chain, and I have said we are going to introduce hidden Markov model, which immediately should trigger in your head, okay, there is something special about this word hidden. This is like a new word that we have introduced. And you would be right. So there is a difference between these observable versus hidden events. So the former we observe directly, and the latter must be inferred. In the context of part-of-speech tagging, what you are observing are the words, and what is inferred or should be inferred and is hidden are the part-of-speech tags. So part-of-speech tags are those hidden states. So hidden Markov model, together with everything else there is in a Markov chain, will also have an additional element, which are these emission probabilities. Each one of these probabilities is expressing the probability of an output observation being generated from a hidden state. This could be really confusing because now I'm saying, given my hidden state, such as a part-of-speech noun, what is the likelihood of having a certain words where the part-of-speech tagging task is the other way around? Given a word, you want to know what the part-of-speech tag is. So yes, it is flipped, but it should be flipped. This is not a mistake, okay? This is just a component of a hidden Markov model. And besides making the first Markov assumption, we are going to make another assumption, which is output independence, where we'll say that the probability of an output observation, meaning in part-of-speech tagging, the probability of a word depends only on the state that produced the observation and not on any other states or any other observation. So here, if you have the probability of observation for part-of-speech tagging being a word, it should depend on all the previous part-of-speech tags seen for the previous words and all the previous words. You will simplify that by saying, and this should be approximation symbol actually, that it only depends on the state. So this is another assumption we are gonna make. All right, so with all of this, we have components of a hidden Markov model if we are defining it mathematically. So this is just the setup. Now, I will show you, illustrate this idea of the hidden state, namely part-of-speech tag emitting a word. And then we are going to put everything together to get an equation that outputs the most likely sequence of part-of-speech tags given a sequence of words by using this kind of illustration that I will show you here. So yeah, be extra focused. I know that things are a little bit funky right now and might be a little bit hard to follow, but this simply is how this algorithm is defined and developed. So let's go through this example. Here you have, remember, for our hidden Markov model, we have these three important components. We have transitions, meaning what are the probabilities from we're going from one hidden state to another. Hidden states are part-of-speech tags. In this toy example, we have only three possible tags in our tag set: determiner, noun, and a verb. And transition probabilities are telling us what is the likelihood of seeing in the next step a noun given, for example, determiner. So that's what the transition probabilities are. Emission probabilities are, remember, what is the likelihood of seeing observation, a word given a hidden state. So here, what are, let's say these are the words in our vocabulary, what is their conditional probability that's conditioned on the hidden state being determiner. Those are emission probabilities, and we have initial probabilities. So for each one of the possible hidden states, what is the likelihood of, when we start our sequence, to seeing this state? So as it's kind of logical, here we have very high probability for a determiner and very low probability for a word. Okay, so this is just, again, repeating three main components of a hidden Markov model. And now I will illustrate this idea of emitting a word given a hidden state. So let's say you start with some special start token, then you would use your information about what is the possible initial stage to be in. And if we go back here, amongst all of these, most likely is that the first hidden state that's going to emit the first word is a determiner. So that's why we see determiner over here. And now, given that there is a determiner over here, we are using our emission probabilities to determine what is the most highly probable word, given that our first hidden state is determiner. So what is the word that's most likely going to be seen here? Nate, if you're speaking, I don't hear you. No? Okay.
Is it
okay.
is it the?
It is the, yeah, and also Elham said it as well in the chat. So because amongst these probabilities, the is the one that has the higher probability, then here we are going to output the. And then next step is to figure out, okay, what is the next possible state, hidden state under these transition probabilities? Let me go here. Oh, we don't have them written. Let's imagine that the next, if you consider probabilities of going from determiner to determiner, from determiner to noun, and from determiner to verb, let's imagine that going from determiner to a noun has the highest transition probabilities. That's why the next hidden state is going to be noun. And then according to the emission probabilities, the most likely word is going to be fed here. Okay, it's not, this is interesting. Yeah. So I'm talking about as if this is deterministic. You always are outfitting the most probable word. It's not like that. You are sampling for this distribution. There is some stochasticity involved. So here, although fed is actually not the highest probable word here, it has been sampled for at this position. And then we can do this as it, you know, in the next step until we reach some, we can introduce some special end token to kind of finish the generation. All right, so this is now this idea of generating text from these hidden states. You can imagine you're generating text, but before you think about what the next word is going to be, you are also thinking, what does it make sense grammatically to have as a category of grammar first, and only then you are generating words. So this is one way to kind of generate text, right? And we are going to use this procedure in a roundabout way to get to these tags from the text itself. Okay, so we have a sequence of observed words, and I'm going to use notation W to denote words. And our goal for part-to-speech tagging or name identity recognition is to produce a sequence of the most likely sequence of tags given that sequence of words. That's the setup for our problem. This is what we are looking for. Now, here we are trying to predict tags given tokens, given words, right? But in that equation, excuse me, let me say this more clearly. In this illustration, we had probabilities of going from tags into the words. So if we wrote that as a conditional probability, it's a conditional probability of words given tags. However, here we have other way around, probability of tags given words. So knowing what you know from your most basic probability class, what can we do to flip these, you know, to have the probability of words given conditioned on tags? And Elham says bias rule, which is exactly what we need here, right? This is like a standard trick in your textbook to just flip what we are conditioning on. All right, so here we just now use Bayes' rule, and now we are in this very nice situation where you can use the procedure we had before, because we had now probability of words given tokens, given these tags. Sorry, the T is throwing me off. I just want to say tokens when I see simple thing. Okay, so let's just simplify this a little bit. First thing is that if you have this denominator that is completely independent of tags, then for finding argmax, this is a useless term. You can put it outside of the argmax equation. Max of this is going to be the same as max of all of this. Okay, it's independent of your choice of the tags, so you can remove it. So this is the first simplification. And then now here we are going to use those assumptions we have made. First assumption we have used our first Markov assumption, right? So the probability of a given tag depends if we are using first Markov assumption. It is dependent only on our previous choice of a tag for the previous word. I should have said that we also there is another step here where we broke the joint probability in a product of conditional probabilities, which is just the chain rule. So it's not written here, but you should all by now know this, that once we have joint probability is the same as maybe I can write it down if I know. Oh, let me open Zoom. Okay, I have learned there is this annotate thing, which might be handy. So let me try. So this thing here is the same as the product of I, okay, equals 1 to n, and then probability of ti conditioned, and can someone tell me conditioned on what?
So without Markov assumption, it will be ti minus 1, ti minus 2 until t1.
Exactly. So all the previous tags, right? And I'm going to write that with this notation when I use this and I, meaning all i's before the current I. So as Elham said, I minus 1, I minus 2, I minus 3, all the way to the first token. First tag, I'm so sorry to keep saying token. I hope that's clear. So this is this notation here. This is referring to I minus 1 all the way to 1. Okay. All right, so there is this product, and then we simplify this product by using the first Markov assumption, which says, well, okay, in reality, you should be considering all the previous tags, but for the simplicity, we are going to approximate that by looking only at the previous tag as written here. Here we have used our output independence assumption, which said, well, okay, here if we had also written this product, it would be the product of word wi, which depends on all the previous tags t1 to ti minus 1, and all the previous words w1 to wi minus 1. But instead of calculating that conditional probability, we will simplify it by saying that the current word depends only on the previous tag. So there are these two assumptions we have made. Okay, and finally, in this final step, we are just going to introduce the notation we had before. Remember, we have introduced two matrices, matrix A with transition probabilities and matrix B with the emission probabilities. So here, remember, the way we define B is exactly through this. So all I'm doing here is reintroducing the notation I have introduced before, okay? That's all that's been done in the final step. All right, so now we have basically formulation of a hidden Markov model. So when if someone asks you what a hidden Markov model is, you can say, well, it is a model where we are finding the most likely sequence, the probability of most likely a sequence of labels given a sequence of inputs. And it's done by calculating the sequence, finding the sequence of labels that maximizes this equation, and you would need to, you would need to introduce these elements as I have done previously when I introduced the Markov chain and then hidden Markov model. So that's what a hidden Markov model is. Now, oh, why is this here? How to remove it? Let me see, can I click some kind of clear situation? No, but I can maybe do this. Okay. Lots of improvising today. Alrighty. So I want to draw attention to you that you do need to find the sequence of tags that maximizes this equation, which means that for all possible sequences, you are going to calculate this value and then retrieve. You can, for example, sort them and retrieve the one which has the maximum value under this equation as the predicted sequence of tags. So remember that there is this argmax. It means that you need to calculate this equation many times, as many times as there are possible sequence tags. Maybe to make that point even more clearer, I will go a few steps ahead and here. So imagine you had a very, very, very simple scenario where you have only two possible tags in your tag set, noun or a verb. Then at each one of these position, for example, here, the Fed raises interest rates, you have 5 words. So sequence length is 5. And at each one of the positions, you have 2 possible options for the tags, namely those 2 that are in your tag set, except for the first position where you only have 1 because of the initial probabilities, which means that in total you have for these sequence length -1 equals 4. For each one of the 4 positions, you have 2 possibilities, which means you have 16 possible label sequences that you can try, right? Like just try to plug in here verb or noun at every position. And if you try to draw all the possible sequences, you will write 16 of sequences composed of noun and verbs. And going back to what I was saying before, that means that for every single one of these possible 16 sequences of part-of-speech tags, you will need to calculate the value under the equation we have seen, and then retrieve the one which maximizes that value. Is that clear? Okay, what is stopping you right now? There is something missing here. So we had all of these, but if I would tell you right now to implement something like this, what I didn't tell you something, and I'm trying to ask you a question, which is basically, what would you miss right now if I told you here is a labeled data set, implement part of speech tagger using hidden Markov model? What would you know how to do?
So my question is, what is the transition matrix before different states?
Okay, now I'm confused. Are you answering my question?
Sorry. I'm trying to answer your question. So I think we are missing the information of transition matrix between different states.
Perfect.
Sorry about that.
Exactly. So I told you should be using transition probabilities. I told you should be using omission probabilities, initial probabilities, but I never told you how do we calculate those probabilities, right? So now, because we are learning a pre-neural approach to all of this, and knowing what you know about N-gram language models, where we also deployed Markov assumption, what is your immediate kind of possibility of how we could estimate these probabilities from a labeled data sets of words and tags. Any quick thoughts? There is a word in the chat which kind of gives away this answer.
I guess we can use some historical data to do some statistics.
Can you specify historical data a little bit more?
Assume we have a large language data set, and we can calculate what is the transition probability given a prior word, and to predict the next word state.
You're kind of getting there, but you are now moving in circles because you said we are going to calculate probability by checking probability. But what is the probability? How could you actually calculate it? So Elham has written in the chat frequency, probably by counting the number of bigrams. And this is how we did it for the N-gram language modeling. We had also needed the probability of seeing a word given preceding words. And what we have done is measure the relative frequencies. We said that the probability is going to be a count of times we see that word with the preceding word relative to something else. And similarly, we can do something here as well, given a label data where for each word we have a part of speech tag. So this is what we are going to talk about next, exactly how to count these things. It's just going to be formally written in a slide or two. And then I want to go over how to quickly get the most likely sequence, because as you've seen in that toy example where we had only 5 words and 2 possible tag set, we already had 16 possible sequences of tags. And now you have seen in the Pantry Bank part of speech tag set that we had over 30 possible tags, and words can be way longer than just sequences can be way longer than 5 words. So you can imagine there are so many possible sequences of tags in a realistic situation. So just plugging them through this equation, every single one of them can be really slow. So we'll talk about how to make that inference faster with another classic algorithm called Viterbi. Okay, let's stop here. Sorry for going over time. We'll stick around for a few minutes if you have any questions for me. Thank you.